All right, if everyone could take a seat within a minute, we should be starting in a few seconds. So yeah, just feel free to grab a seat, make yourselves cozy, and we will start our event today. Okay. All right, cool. Closing the doors, and all right, let's get this show started. Hi, everyone. Thank you all for coming to our event today, where we'll be celebrating the anniversary of the foundational research paper, Attention is All You Need. For those who don't know, Attention is All You Need was a paper that introduced the transformer architecture that powers products such as OpenAI's GPT-4 or ChatGPT, which many of you probably have heard of. And yeah, it was written by a team from Google Brain, Google Research, and UFT in 2017, and has continued to inspire other influential machine learning models, papers, and other academic concepts. Today, we'll be celebrating with some guests who will be explaining how important the paper is also in the industry. So joining us today is Luis Serrano, Developer Relation Lead at Cohere, who will be graciously presenting a talk on a friendly introduction to multi-head attention models and a bit of what Cohere does and how they kind of fit into the realm of transformers and like machine learning here. So without further ado, I'll pass the mic over to Luis and let's get this event started.
Hello, thank you very much for the invitation to the club and to Ashley. It's so nice to be here. Actually, very special because Waterloo is my school. I went to Waterloo for math many years ago, before data science existed, and I had a great time there. Would love to be there in person, but actually today I couldn't. But maybe next time. Yes. So yeah, let me start by sharing my screen. And actually, I'm wondering if I share. No, I feel like I am able to.
Okay.
Okay, do you see my screen?
Yep. We're able to see it here.
Okay. So, yes. So I introduce myself. We'll talk about attention. My name is Luis Serrano, Developer Relation Lead at Cohere. And so sometimes, by the way, this is an informal chat, so feel free to ask me questions. I see people are in person, so you can just kind of yell the question. Don't even need to put up your hand because I won't see it. I will also ask you questions. So, and by the way, this is a very friendly introduction. So it's a very friendly talk. But I'll tell you sort of how I see attention. Before I get there, I'm going to tell you, as I promised, a bit about Cohere. Whoa. One sec. You see one screen, right?
Yes.
Okay. So yeah, I'd like to point you to this page, dashboard.cohere.ai. That is where you can play with all the models. In case you haven't seen it, it's really fun. You can play the models, put in your data, even just type it in or put in a file and play with the main endpoints that we have, which are language generation. So that's a big thing, of course, as you've seen, similar to like ChatGPT and all that stuff. There's chat there's summarization, just put a big text and it turns it into a small one, or like it gets the main points of it. Copywriting, you can put a little prompt and it expands it, or chat, a generative chat. That's like a chat bot. But generation is not the only thing we do. Actually, the biggest bet we have at Cohere is search, because as you've seen, like these generative models hallucinate a lot, right? Or just say things that are completely confident but completely wrong, and that's dangerous, right? So we like to power generation with search, and not just keyword matching, but actual neural search or semantic search, which keyword matching can also be a problem because you may get the right words from the query, but completely wrong meaning. And so neural search uses embeddings and different things like re-rank or retrieval augmented generation, which I'm more than happy to talk to if you have any questions, to actually find good search results. And then if you put that together with generation, then that's great because, right, you ask a question and first it searches to get the right answers. And out of that smaller set, it generates an answer. So it's much more exact than if you just answer from the entire internet and you may answer anything. And other things are like classification, right? Which you may be thinking, why classification if classification was, I think, 10 years ago, right? When we started classifying text and images and we were like, wow, that's amazing. And now it's super easy. But actually, if you have a good embedding, a good LLM, you can do classification with very, very, very few examples. I remember 10 years ago, I would just train my models with my sentiment analysis models with like thousands and thousands of examples. And it'd be like, all right, now I can train one with four examples or 5 or on each class, and it works really well. And that's because of the embedding. So basically, we have what we do at Cohere is we have all these endpoints for developers to use, for companies to use, and I'd love for you to take a look at them. So dashboard.cohere.ai, and I think Ashley later today is going to talk about a search, right? A search application with LangChain AI. So you'll get to see them in action. Another thing I want to point to is this project we've been doing. It's called LLM University, LLM.university. That's the address, LLM.university. And in there, we teach everything about all of transformers, right? All of the transformer models, attention, et cetera, and basically in a friendly way. Like basically, what I'm going to talk today comes from there. And also we have code labs, we have a bunch of stuff. We're going to add stuff on deployment, text generation. We have text generation, text representation, all that stuff. So I definitely invite you to check it out. And I think I may have done this backwards. Sorry about that. Let's fix this. So of course, we're celebrating this anniversary of this wonderful paper. Attention is all you need. And one of the co-authors is AIAYN Gomez, which is actually the founder of Cohere. So this is pretty much what kickstarted the company, right? This paper. And so I've been reading this paper, and it's a wonderful result, and it's a wonderful construction that really is what made computers talk the way they talk now. This is really what did it, and the concept of attention is really what made it special, right? Because we already had models that could predict the next word in our phone, right? Like if you go on your phone and type some words, and then the phone kind of recommends the next word. Like if you say hello, how are you, it recommends doing, right? But those don't capture context, right? They just kind of check what word would fit best according to the previous words, but it doesn't capture the entire context of the sentence or the text that you're talking. When they did attention models, in particular multi-head attention, that's what really did it. That's what really got these models to be able to talk and keep a conversation for a long time, right? So I started reading this paper, and I have this what I want to share to you today is that I was having this I have this condition where I just can't understand research papers, and I think that condition is called being human, because I've met most people that who just can't understand research papers because they're written in complicated language. And so I went here and I said, okay, what's attention, right? On the left we have scale dot product attention and multi-head attention, and so this is a formula for attention, and this is the one for multi-head attention. So this was my reaction when I started seeing these formulas with these Q, K, and V matrices called query, key, and value. Luckily, I got my friends to bug them. So I started asking my friend Jay, my colleagues, Jay and Joao, and pestering them for a long time until I think something clicked. And so I'm going to show you what clicked, which is sort of my way to see attention. It's slightly different than the one in the paper. You see some matrices K, Q, and V, and I don't like to see matrices as arrays of numbers, because to me that's like seeing a book as an array of letters. You know, there's a lot more to it. I like to see matrices as linear transformations and things where in the plane that move. And so I try to explain the whole attention by things moving around in the plane. So that's what I want to share with you. And as I said, I would love to, if you have questions, comments, feel free to stop me at any moment. So first, I'm going to ask you I'm going to do a very easy quiz, just to be on the same page. Here's an embedding. By the way, I can't see hands, but how many people have seen embeddings? Can somebody tell me how many hands go up?
All right, I'm seeing 3, 4 hands. All right, let's.
Oh. Great.
All right, is anyone gonna? Okay. Sweet.
So embeddings are the most important thing, in my opinion, the most important thing for large language models. And the reason is because it's where the rubber meets the road, right? Like it's really where the translation happens between humans and computers is in embeddings, because embeddings assign to every word or to every piece of text a bunch of numbers. A bunch of numbers is a list of numbers, or a vector. And the better embeddings are, the better models are, right? The better, if tomorrow somebody comes up with an embedding 10 times better than the previous ones, then the models are going to be 10 times better, because that's when it goes from human talk, which is words, to computer talk, which is numbers, right? We're good at words, computers are good at numbers. So the better this bridge is, the better for everybody. So I like to see embeddings, for example, as 2 numbers for a word, right? I'm assigning 2 numbers because one is the horizontal X coordinate and the other one is the vertical Y coordinate. And so, for example, the word banana is assigned the numbers 6, 5, right? Because it's 6 on the horizontal and 5 on the vertical, and strawberries 5, 4, etc. So the quiz that I have for you is, where would you put the word apple? On A, on B, or on C? What do people say? Feel free to yell answers. Or
anyone feeling confident? We're hearing a lot of C's. Got 1 A.
1 A, wow, nice. Some C's.
Mostly C's from what I've been hearing.
Okay, yeah.
Last call. 3, 2, 1. All right.
Final answer.
Seems
okay.
like it, unless anyone wants to butt in. C seems to
Great.
be it.
Yeah, I mean, it could go anywhere. I would put it more likely in C, and that means the coordinates be 5, 5. And the reason is because embeddings have that particular property, right? Like if you have a good embedding, has close words go to close numbers, right? So if 2 words are very similar, then they would go to very similar numbers. And of course, it's not just 2, right? It's not just 2 numbers per word, but it's lots of them. So actually, one of the embeddings we use at Cohere, it has 4,096 numbers per word. So you can imagine that these describe the word really well. And actually, if you start looking at embeddings more carefully, like each number actually is a property of the word. Maybe the color, maybe the size, or maybe something more complex. Maybe a combination of properties, or maybe something the computer sees a pattern and we don't. But the fact is, if you try to imagine embeddings as a bunch of numbers, fixed set of numbers that pretty much describe each word, and that if you have similar words, they go to similar numbers, then you're imagining them correctly. And of course, the one in the left, I can picture it as points in the plane. But the one in the right, you can picture it as points flying in a 4,096 dimensional space. So whichever you want to imagine them. So, okay, now that you did so well in quiz 1, I'm going to have quiz 2. And so there's going to be a few questions. So feel free to just yell one answer, and then I'll continue. So you're going to tell me top right or bottom left. So if the drawings are not clear, there's a strawberry and an orange on top, right? And then there's a cell phone and windows on the bottom left. Okay, so you're gonna tell me top right or bottom left. Where does cherry go?
All right, what do we think, audience? Top right?
Top
Mostly
right, all
top.
right. Android.
Bottom left? Seems
Yeah,
like.
I love it. Bottom left, I feel the energy. Laptop.
Bottom
Bottom
left?
left. Banana.
Top right?
Top right, you're on fire. Apple.
Right.
Middle.
Oh, someone saying the middle. Is that our final answer, audience?
Final answer, yes.
The
Correct. Because
Oh.
I don't know if it's an apple, the fruit, or an apple, the brand. And so if I knew, then obviously the apple would go in the correct place, but I don't know. The computer has no idea. So it kind of has to put it in the middle, right? And no matter how good an embedding is, it's not gonna know where to put the word apple because it's just, it has to assign numbers to each word. So it's the embeddings have a problem. They have this sort of bottleneck. And so we need a solution for that. And the solution is attention. What we're gonna do is we can no longer look at words by themselves. Now we have to look at words in their context, okay? With the words that are neighboring. So I have to look at the entire sentence. So I could say, for example, please buy an apple and an orange, or Apple unveiled the new phone. Now, who can help me? What are the words on the left sentence that kind of hint to you that you're talking about a fruit? Orange, right? Correct, perfect. And on the right? Phone, right? So we got these keywords that we're gonna use to tell us what's happening, right? What apple are we talking about? And what we're gonna do is literally use those words to pull the apple, okay? So if I have my embedding here and the orange is here and the phone is here and the ambiguous apple that we have no clue what kind of apple it is, then we're gonna move the coordinates of that middle apple towards orange or towards phone based on the sentence. So for example, in the first sentence, I'm not gonna use the coordinates for apple. I'm gonna take orange and pull the apple in that direction, okay? And so it's gonna go here. And so I have a new set of coordinates. I don't use the coordinates in the middle. I use a new set of coordinates for that red apple there. And for the other one, I'm gonna use the word phone to pull the apple. And then for that sentence, I'm not gonna use the coordinates for apple in the middle, but I'm gonna use the new coordinates for apple. So if, for example, if my orange is at the point 1111 and my phone is at the point 12 and my ambiguous apple is at 67, then I'm not going to use 67 for apple, but in the first sentence I'm going to use 8.5, which is the one I'm pulling towards the orange, and in the second sentence I'm going to use the numbers 4, 5, which is the one I'm pulling towards the phone. Does that make sense, or is there any questions?
Seems like everyone's got it. All
good, perfect. And of course, this step is get done a lot in transformers. In the transformers, you have a big neural network where you apply attention at pretty much every few layers. And so if you imagine doing this a lot, the words are gonna kind of move to the right place. But this is just one step. But question, how did we know that the correct word to use was orange? I mean, we know, right? We know as humans, but the computer doesn't know. And if it did, it would be way ahead, right? So the computer doesn't know that orange is the word that it's supposed to use to pull it. So it kind of has to use all the words, right? So it has to use all the words. And we're going to do something to make sure that orange is sort of the one that pulls it the most. And what we're going to use is some kind of gravity. Okay, I like to see this as gravity. So imagine that the embedding has the words like this. And if it's a good embedding, you know, apple and orange are close by. And so they have a strong gravitational pull, right? You see, when you're close, you have a strong gravitational pull, whereas the others have like very low gravitational pulls. And so Apple's gonna move to all the words to please, buy, and, but not as much as to orange, because orange is closer. So you have a bias on words that are similar, pull each other more, right? And so it just kind of moves more towards open. And check this out. You can do it. You don't just do it for Apple. You do it for all the words in the sentence. Okay, you do it for all the words. And so, you know, if you're talking about fruits for a while, then you kind of have like a little galaxy of fruits here where all the words get pulled. You see, so like attention is that you pretty much gravitate the words until they come close, and if you have a strong topic, it's a galaxy that pulls everything in. So I look at it as like, you know, planets, right? Like the Earth and the Moon have a strong gravitational pull because they're close, whereas like, you know, Saturn and Pluto and Jupiter don't really pull it that far, so they end up close words end up pulling each other more. Is that clear? Sort of how that is seen. Like you end up moving the embedding and the words come closer, and that's how you sort of, your context becomes something spatial, right? Like you kind of gravitate towards a certain place, and that's where the context of the text is, as opposed to like all over the place, right? Any questions so far?
Doesn't look like it.
All good, perfect.
Okay.
So now I have a question, and I always ask my questions kind of as loaded questions. Do you think one embedding is good enough?
Is one enough, audience? Now we're getting a few, what is it, no's? Good amount of no's,
Yeah.
actually.
A lot of no's, because yes, I definitely a loaded question. If it was yes, and I would finish the talk, I would be like, okay, thank you. Actually, she doesn't want it. The answer is no. The answer is no. We can do better. We can actually do better, and that's why it's called multi-head attention and not like one head attention, right? The multi is because we're going to use a lot of embeddings. So ideally, we'd like to have a lot of embeddings. So I have another quiz for you. I'm going to show you 3 embeddings. This embedding 1, embedding 2, and embedding 3. And I would like you to tell me which one of those 3 is the best embedding for our particular pair of sentences. Remember this, there's an orange and a phone and an ambiguous apple.
Best
So 1, 2, or 3.
Okay. Thinking a bit here, and it seems like 1 is our audience's answer.
Great audience. You're doing a great job. Yes, 1 is the best one. And the reason is because it pulls the points apart very well, right? Like, do you see it? It kind of like separates the apple pretty well from the other apple. Whereas like the second, I missed it. I was gonna ask you what's the worst one of the two of the two remaining ones. Which one is the worst one?
Worst one. A bit of thinking. Got 1 second. Someone said it's a second.
1 second, yes.
We're still thinking a bit, it seems. But looks like that's the only answer we're getting from the audience.
Yep.
1.
Great job. The worst one is the second one, because it doesn't really separate the apples, right? Like if I pull the apple and the other apple here, they still look very similar. So it didn't really do a good job, right? The first one separated them really well. It sent them to different places in the universe. Yes, the second one is not so good. And the third one is just an okay one, right? Like it kind of separates them. So it's so-so. So the idea is to use a lot of embeddings, and chances are some of them are going to be very good. Some of them may not be so good. Some of them may be like, you know, really good for fruits. Some of them really good for technology stuff. Some of them really good for sports. Like it just happens that, you know, different embeddings do different jobs, and we'd like to get the best of it. So there's a problem. The problem is that I can't just go buy an embedding in the corner store. They're hard to do. They're hard to they're you know, basically it takes a research group or a company to build a big embedding, and you can just build a bunch of them, and they may have different dimensions, right? Different length of the vectors. Some of them may be 4096, the other one's like 1000. So how do you combine them? So it's hard to get a lot of embeddings. So what can we do? What we can do is we can modify our existing embedding to build other embeddings. Okay, so we can take our original embedding and just kind of warp it around and move it and stretch it and stuff like that. And that's where linear transformations come in. So if you're taking a linear algebra class, You may have seen these linear transformations. You may have seen them as matrices. I hate to see them as matrices. They actually are a geometric thing. So I'm imagining this dog here, and the linear transformations can be several things. It can be rotations. So you can rotate the plane, rotate your embed, or think of it as space, right? Or you can stretch it like in any direction. I'm going to show you the stretching sideways and the stretching upwards. And there's a third linear transformation, which is kind of weird, which I imagine is like, imagine if you have a very big book on a table and it's stuck on the table, and then you kind of push the top part of the book, and it becomes like this, like a shear. That's another linear transformation. And they're all represented by simple matrices. And so you can combine them by multiplying these matrices, right? And that's where the matrices that I told you at the beginning, right? That key query value matrix, that they really are doing this. And when you have any combination of matrices that you multiply, then you end up with pretty much any warping of the plane, right? And so you can think of it as you have two main vectors there, the yellow one and the blue one. And if you just send the yellow one to any vector and the blue one to any other vector, and then the rest kind of follows, like the main square becomes a parallelogram and the rest of the plane follows. That's a linear transformation. So why did I get to linear transformations? The reason is because that's what we're going to use to get new embeddings from existing ones, right? So let's say my original embedding is this, and this embedding is okay, right? And I can twist it around to get this one. And then I can also twist it around to get this one. And these are very similar to the ones we saw before, right? So quick check. Which one's the best, and the best of these three?
Best of these three. I think I'm here in a few thirds.
Correct. Awesome. And the worst one?
Worst one. Here in second.
Yes, you all rock. Exactly, right? So I twisted my embedding and I managed to get a good one and a bad one. And so the first one is an okay embedding. The second one is not very good embedding. So this one's bad. And the third one is a good embedding. And so I can score them. Imagine if I had a way to score them. This part is part of the big transformer. You can train these scores. So I'm not going to get into detail, but imagine if I could score them. So I could give, a decent score of 1 to the okay one, a very small score of 0.1 to the bad one, and a really good score of 4 to the great one. And now I got it, right? So now we can go back to this multi-head attention thing over here. And the way I see it is on the bottom, you have, let's say, your sentence come in, and you have your embedding. So you use the key and the query matrices to transform this embedding in different ways. And then you use the scores. The values are the scores that you give this embedding. So I give them scores of 1 to the good one, 1 to the okay one, 0.1 to the bad one, and 4 to the great one. And then something called scale.product attention. What I do is I sort of give them that weight. So I multiply them by their respective weight. So I put more emphasis on the fourth one, on the third one than on the second one, and okay emphasis on the first one. And then concatenation means I combine them. So I add them, obviously the third one multiplied by 4, the second one by 0.1. And so I get something that is really good, because each embedding is weighted by its score. So the good ones are more important. And so I get an embedding that has context. And so that's how I finally made some sense in my head of this multi-head attention. And then that's a big part of the transformer, which is another story. But then basically, if you've seen neural networks, a transformer is a big neural network that guesses the next word at every time. And somewhere in the transformer, you have this attention step working in your favor. And I think that's all I have. So before I get to questions, let me tell you a few things. So don't forget to check out LLM.university. There's going to be a lot of lectures like this one, labs, etc. So it's LLM.university. Super recommended. And as of myself, I have a bunch of stuff out there. So if you want to check out my YouTube channel, it's called Serrano.academy. I have a explanations and videos on machine learning, all cartoonish because I can't understand formula, so it's all in a cartoon like this one. So definitely check it out. Serrano.academy. That's my Twitter, also Serrano.academy, and my page is the same name, where I have blog posts, videos, etc. So yeah, you should totally check it out. And I think that's all I want to say. So I don't know if you have any questions.
All right, sweet, sweet. Can we give a round of applause for our speaker here today?
Thank you.
Thank you, thank you. No one has any questions. Oh, we have one question here. Yeah.
So
Yes.
how of the x, y coordinate or the higher dimensional coordinates of the text are measured?
Okay.
How is the score? How are the scores are measured?
Okay. So audience member asked, like, how are the scores essentially calculated for each of those?
Great question. Yes, great question. Yeah. So here's the thing. In the neural network that is a transformer is just a big neural network, right? And you train the weights of the neural network to sort of find the next word normally, right? What you do is you put attention layers in between, and these attention layers have the scores and the transformations as three matrices, right? As the value matrix, the key matrix, and the query matrix. And so you start with random values for all those three matrices, and then you train them as you train the neural network. So you see what I mean? Like if the neural network gets, as it gets trained, all the weights get recalculated, and so do the weights of the key query value matrices. So for example, if a word worked out really well or poorly, you back propagate and you sort of change these weights around. So the values, the transformations, and the scores of the transformations get trained with the neural network as you go. Yeah, so that's a bit vague answer, but that's how it is.
Right, an awesome answer. All right, cool. We got another question. Yeah.
If there exists a concept is very strongly presented in a particular language, and all of this information is fed in, for example, whatever. How do we get rid of biases?
Okay, yeah.
Like, for example,
Okay, cool. Yeah, audience member asked a cool question. So I guess for like a lot of these concepts that get put into the embeddings, like how do we remove bias from them? Like how do we say like, okay, a doctor isn't always male, nurses isn't always female?
Yeah, that's a huge thing and very hard. Yeah, I mean, anything that replicates human behavior is awful, right? Like sexist and racist and everyist, because that's how the data is and that's how people are. So definitely, these are hard things to overcome. The main thing is in the data and in the models. So in the data, you just have to clean up data as much as possible. Try to remove biases. Of course, they're not always removable, right? Like for example, if you have resumes, you may remove demographic data, race, gender, etc. But then the model may pick up biases by saying, oh, if I have the combination of this and this and this and that, that's equivalent to race or gender or something like that. So it's hard to really remove, but you can just clean up the data as much as you can, and then with the models as well, you can have sort of detectors for certain. For example, in a language model, you can have detectors for hate speech or for anything that's negative, and try to put barriers there. So I would say the data, the models, and then also I always make advice of just don't let the model run everything, right? Like don't just blindly put the model to work and do it. And you have to always use it as a tool. And if you use it as a tool, at least there's some human input to actually make the right decisions. But yes, you really pointed out something very important. Bias is something that's a huge problem that needs to be addressed much more if we can figure it out.
For sure, for sure. All right, I think Blue Soda had his hand up.
So right now I see it like these transformer models are like really large, and right now the model is like the company owns like the big model and then provides an API for like other users to use. What in the future, like, do you have any idea if this kind of model will change, or will somehow these language models be able to be used just by like the user itself of this kind of structure?
Okay.
Could you repeat? I heard most of it, but I missed a little bit at the end. I'm not sure you can repeat it.
Yeah, sure.
Will these large language models ever be able to be like fitted into a personal computer? Or
Got it. Ah, that's a very good question. Yeah, I mean, right now, these models are huge, and really, what makes them work is that they're humongous. So before we could fit them in the personal computer for 10 years ago, you do an image recognition or a sentiment analysis, and it would fit anywhere. Right now, they're very big, and so you need a lot of computing power to train them. So in a computer now, I think it wouldn't fit, but who knows if we're getting bigger and bigger computers, maybe we'll be able to fit one of them in a personal computer. But then if we do, then probably with the companies will be able to train much bigger ones that would do a lot more. So I think if your state-of-the-art models are built in the biggest supercomputers with the biggest data centers, that they're always going to be ahead of the ones you have in your personal computer. So as of right now, yeah, I think it's mostly API usage. Like you can call the API and then you don't have to store all the weights.
All right, perfect. Let's get Black Shirt. Next question.
Yeah, so you mentioned earlier about how like the real embeddings that are behind like the chatbots are really populated and they have a lot of words. And then how do you deal with the super populated embeddings? Do they replace other words if they use those sort of words? Something that's on
Yeah, there was a lot of echo. I wonder if you can repeat it because there's a lot of echo.
how do you deal with populated embeddings? Like which words take priority over others when there's a word interface where you're trying to move?
Like sparse embeddings?
When it's really populated. Like when there's a lot of words, I'm guessing if you want to change the place of a word, there's a value already there. How do you deal with that?
Like from what I understand, like how do you like prioritize some embeddings over others, I guess?
Yeah, good question. Yeah, so there's different types, right? There's as you said, the really populated embeddings where the vector is pretty dense, and there's others that are really sparse, where like it's a bunch of zeros and stuff. But yeah, different embeddings work for different things. An embedding that works really well for a chatbot may not be so good for search, or for a classifier, etc. So you really optimize them and fine tune them. So for example, a search application uses a search specific embedding that you will use, and then you sort of move the points around so they work better with search by training it with question answers, with data sets of question answers, etc. So yeah, every embedding has its own applications, and you optimize it for what you need. I don't know if I answered your question. Did I?
Think so. Yeah,
Okay.
I would suggest. All right, cool. If none of the audience has a question, I actually have a question myself.
Sure.
And I'm just wondering, like, I guess in your kind of opinion, like, what are some like new kind of breakthroughs happening within the field right now that I guess we should maybe keep attention to coming up?
Yeah, I struggle to keep it every time there's more stuff. To be honest, this whole like transformer thing caught me by surprise. I didn't think they were gonna be talking so well. DALL-E, like image generation, also kind of caught me by surprise. I was kind of keeping up with things, and then all of a sudden I start drawing these amazing things. I mean, yeah, like just video generation is gonna be big. I think soon it's gonna work well. And I think just a lot of, I think with this text stuff like that means the embeddings know a lot. And when the embeddings know a lot, it's kind of like having a human that knows a lot and you just teach it things. So a lot of things kind of come out of there. For example, you can do like, you know, PowerPoint presentations by just telling it what to do. And, you know, just basically we're dealing with computers that are like with models that just kind of know reality much more, right? So anything that a human can do, like, you know, sounds, songs, movies, can now is now one step closer to do, because it's in the embedding, right? Like it's the information is there. It's just a matter of how to, you know, putting the training data set and getting things out. So I wouldn't be surprised if a lot of computers can all of a sudden start doing a lot of stuff. And what I think is that they're going to be able to do a lot of our sort of rational tasks that are repetitive, right? So they will be able to do all of those, and we're going to have to move up to higher decision making, higher level decision making. Yeah. So and actually, I was talking to Ashley earlier today about quantum computing, right? I think there may be a breakthrough on quantum computers, at least on the generative side. If they grow a certain amount, I'm definitely keeping an eye on those, because they may have a big moment soon. Who knows? Yeah.
Right, sweet. Yeah, good to keep in mind. Oh boy. Okay, we'll take the last two questions here before we hand
I
it
don't want to get too
over.
much into Ashley's talk. I feel I can take
Yeah,
some.
for sure.
Okay, but I am enjoying the question. So yeah.
Yeah, no, it's been awesome. Audience members have been awesome. So yeah, white sweater.
The XY plane shown at the beginning seems to be a clustering problem or a k-nearest neighbor problem. But when the embedding grows very large, there will be a curse of dimensionality. So how does transformer handle high-dimensional data?
Great question. Actually, not just for clustering, but for everything, right? For search, for example, how do you do search? You just search. You put your sentence and find the closest sentence. So nearest neighbors, which sounds very easy. It's actually very hard when you have a lot of numbers, a lot of dimensions, and a lot of points. Same thing for clustering, obviously. There are a bunch of shortcuts for dealing with very large spaces. So for both clustering and for nearest neighbors, you can do, for example, there's different. One of the shortcuts is you sort of like cut your space into little chambers, and then all of a sudden, if you're looking for a nearest neighbor or for a clustering neighbor, you only have to look in the chambers that are adjacent. You don't have to look at all the pairs of points, right? So that cuts the running time in a lot. Or you can start doing some kind of hierarchical clustering when you just pick a bunch of points first, like some random points, but not that many, and do your clustering there. And then as you add points, you see what they're closest to in the previous hierarchy, right? Like I pick 1,000 points and I do clustering there. And then when I throw in 10,000 more, I only have to compare them to the ones that were there before. And then I throw in 1,000,000 more and I have to compare them only to the ones that are before, as opposed to all each other. I don't know if I was very clear there, but the fact is there's a bunch of shortcuts to deal with with humongous data sets in high dimensional space.
Okay, cool.
Thank you.
Yeah, all right, last question here.
So you said that the model used like a linear transformation. I was just wondering if is it necessary to be linear, or you can make the dimension like larger on the model so you can separate it better?
Were you able to hear that,
Can you
Luis?
say it to half of it, because it was broken? It sounded, I heard the word linear. Can you say it to me?
So you said that the model used like a linear transformation, like a linear transformation matrix, right?
Yes.
So I was just wondering if you can like project it into like a higher dimension or a lower dimension, so that you can separate like between two things better. Or
Yes. Good question. I kind of some details I left them under the rug. Like I said everything was 2-dimensional, right? Like I said, you go from 2 dimensions to 2 dimensions. But in reality, these matrices don't need to be square, right? They can be rectangular, and these matrices are actually rectangular. The query key and value matrices are not squares, but they're rectangle. So they linear transformation one space into something of different dimensions. And my guess is that they're smaller, but I have to check. But what you do is, yeah, you take your embeddings and you linearly transform them, and then you get a smaller dimension, and then deal with stuff there. So yes, you're definitely projecting at some point. I don't know if I fully answered your question. Did I?
Looks like you did. Yeah. All right. Sweet,
Okay.
sweet. Okay. I think this should be enough for our portion. Don't want to get into Ashley's time too much. Yeah. Again, thank you so much, Luis. And looks like
Thank you all. I'll
me
stick
and the
around a
whole
little
audience.
bit.
Yeah.
Huh?
Sweet, sweet.
Okay.
It's just. I was just saying. Yeah. It looks like the audience and I all loved it. Yeah. Thank you again.
Oh, thank you very much. I really love the audience too. You answered all my questions and did very well in the quizzes. Congrats.
Hey, sweet to hear. All right then.
Thank you. It's a pleasure.
Perfect.
Before I get started, I just wanted to ask if cake has arrived yet. If not, I'll get going. But if so, I don't want to hold people up.
There
Yeah,
was
I
cake.
think it's there is. It looks like it's on its way, but I don't know what the ETA is. If you want a quick break.
I'd say I'll get started. Interrupt me when cake comes. People can grab some cake, and then we'll continue on. It'll be pretty chill on my end. So just pop in once the cake comes, so people can go serve themselves.
All right.
Thanks
sweet,
again
sweet.
for the great talk.
All right.
I'm just sharing my screen.
Cool.
So hopefully you guys have gotten pretty excited about the idea of using these large language models now through APIs. I think at least I have. So we have the perfect thing to follow this up with on showing you how you can actually do that. So hopefully this can kind of be useful for anyone from beginner data scientists, intermediate data scientists. If you haven't used these APIs before, they're pretty easy to use and are pretty low code needed. So even if you're not a pro Python programmer, that's absolutely okay. You'll just be following along some little bits of code with me. So the goals are just to understand how these large language model APIs work and why they're useful, to set up an account and an API key for Cohere's API that we'll be using as an example to walk through these ideas. And then by the end, I hope that we can use Python and the Cohere API to do some text generation, classification, and summarization, maybe even some more. So why should you care? Hopefully everything before this has been motivation enough, but large language models are becoming extremely powerful and interesting, and you can, of course, try and train your own, but that's a huge endeavor that you might not have the resources to make something nearly as good as what you can access through one of these APIs, and you can download pre-trained ones and just host them on your computer. But again, that takes quite a lot of resources you might not have access to, and they might not be as good as what you can use through these APIs. So the third thing is you can, of course, use these online playgrounds. They're super useful. And like most people using ChatGPT, that's kind of what you're doing. It's like an online way to interact with it. There's just some limitations to what you can do with those tools. And it's always manual inputs. So there's no way you can easily go and integrate that with like an application you're trying to build for someone's phone. So we're going to do a lightning round through some of the lingo, just so everyone's on the same page before we dive into any of the code. First of all, what is an API? It stands for probably the most broad thing ever, application programming interface. But I really liked this analogy they had of how an API is similar to a waiter. In this case, that you're at your table, you want to stay at your table, like continue your other conversations going on, but put in an order for something to eat. And so the waiter will come and get your order and then bring it to the kitchen that's located somewhere else. They'll prepare your order, and then the waiter will bring it back to you. That's exactly how most of these APIs work, where you are sitting at your computer. All it needs to do is be connected to the internet most of the time. You send over a request to an API. It goes to the server where the model is actually hosted, runs the prediction that you actually want to get, and then brings that back to you. So it's a lot easier than if you had to run this all yourself and have your own kitchen. An API key is a unique identifier that grants you access to use the API, and they're usually generated by the service provider themselves. So you don't make yours. The people you're trying to use their model, they make you the API. So that's what we'll be doing on Cohere's website in just a sec. The purposes of API keys, I thought of 4 here. The first one is authentication. So it tells them who you are, and it says that this is the person, this is related to your account. Authorization, so it makes sure that you're only doing what you should be able to do. So if you have a specific plan or specific access to things, that'll be incorporated into the API itself. And then usage tracking, so it can tell what people are using what, and how many people are using things. That's really useful for this 4th point of rate limiting. So with a lot of these APIs, if you're using ones that are made freely available to you, there's often some sort of limit on how many calls you can make per minute. And they track that by knowing your API key and what previous calls you've made. So prompts and completions are another kind of core thing you'll hear thrown around a lot. A prompt is just basically the question you're asking a large language model, and the completion is the answer you get from the large language model. So here's a really good image we grabbed from Cohere's website that basically just shows how the prompt's the input and the completion is the output. Now, prompt engineering is just when you really master this process and you can get really specific at the prompts you give. So often you're putting in some background context that you want the model to know, and also potentially some examples of how you want it to answer your question. And that can get you really good and really specific answers to your question without having to go into the model and change any of the weights of the layers. An API endpoint has been also something that's been brought up, and it's a place the API sends its request to. So if you want to generate text, what we're going to do is we're going to use an endpoint called generate that'll generate the text for us. Now a token, we've already covered a little bit, but it's just the kind of small bits of words that the large language models understand. Just as humans, we understand words. Sometimes those words are chunked up into even smaller things, like this large word here I have on the right. Establishment is a pretty big word, and it can get chunked up into 3 tokens, as kind of shown in this example there. On average, one word is maybe about 2 tokens, but it really depends on the word. Something like the would just be 1 token in most systems, but something like establishment might be easily 3. So temperature is one of the things we'll be playing around with a little bit, and it's just a measure of how to control the randomness of the outputs of these models. So a temperature of near 0 is good for when you want pretty much always the same result, and that's something you're going to want if there's an exact answer to your question. Then a temperature of about bigger than 0, maybe let's say 5 is great if you want always different answers, and you might maybe want to be doing more creative tasks where there's not just one right answer you're looking for. Now, I think this is the last piece of lingo we're going to touch on. It's just fine tuning. So this is when you really want to customize a large language model that's built for, let's say, like a generic purpose to something super specific you want and that you can't just do by doing some good prompt engineering. So this will often mean you start with the large language model that's been trained on a lot of data, and you don't need to then use a bunch of data. You just need to have some maybe very specific examples of what you want to do, and then you can tune some of the weights in the model so that the model will then permanently act a bit more like how you want it to. So in terms of the cool applications of this, the endpoints we're going to talk about in the notebook I'll be pulling up in a second are generate, which could be used for some cool things like generating a story or a cover letter, and then classify, which you can have little bits of text that you classify with different labels to, let's say, do some sentiment analysis on different reviews you're getting, or detect what's maybe some harmful speech you see online. And all these examples are things that have been done before, and the summarize one I thought was really cool. So for the summarize endpoint, someone made a Discord bot that will go and summarize all the missed activity. And of course, like, you'd want to go and read some of it yourself if you're actually interested. But I don't know about you guys, sometimes I just have like a lot of Discord activity I'm just going to scan anyway. And it's a cool way to get to the end by just using something like that. And then re-rank, which is part of all the search stuff that we have been talking about, where it can go and retrieve documents that or little bits of text that are really relevant to a question you want to ask, so that your model's not just making stuff up. And the last thing we'll touch on in the notebook is this relatively new framework called LangChain that helps you build applications on top of large language models. And the nice thing is it works with a bunch of different large language model providers. So you can work with a bunch of different things, whether it's Cohere stuff or OpenAI. It's compatible with quite a bit. And it can allow you to do more advanced use cases more easily. So a couple examples of this are that you can plug and play really well with different LLM providers. So if you do create an app and then decide you want to switch the company or model that you're using, it's very easy to do it through there, since the code can kind of just adapt for you. And then it has these built-in prompt templates. Like, let's say you want to have a chatbot interaction. It has some of these that automatically set up that interaction for you, so that you don't necessarily need to do all the coding. Then in a similar way, some of the code is already built out for you if you want to be like querying a knowledge database to provide answers to your question with like a link to where that answer came from. So there's some really cool code they have. And the one I might point you to specifically that I just saw earlier today and I thought was really neat was they have these agents that they can let the large language models have access to, where you can allow it to use something like a calculator. It's famously probably known that if you do ask a kind of complex math question to a large language model, it'll answer with a lot of confidence and it'll like very likely just be completely wrong. But with these things, it can give them access to some simple tools that then make it so it can potentially be more likely to get the right answer. So I've set up a Google Notebook we'll head over to in a second. I have the link up here. Hopefully people can pull it up, and maybe someone there in person can kind of let me know if there's been any issues with people pulling it up.
All right, sweet, sweet. Give the audience some time to pull that up. Make it 30 seconds. Yeah. Is everyone able to pull it up all right? So we're getting a lot of thumbs up, yeah?
Okay, perfect, thank you. So before we hop into running any of the code cells here, there's two things I'm gonna ask you to do. The first one is just go under File and then save a copy in your drive. This will give you a copy of it, even if I choose to delete this or move it someday. And you can also edit it yourself. So if you wanna try some slightly different things, super useful for that. Now, what we've talked about a bunch before, you need an API key to work with any of these things. So there's a link here that's hyperlinked on the word here that you're going to press, and it'll bring you to the sign up page for a Cohere account. You'll have to enter an email and a password, and then you should be greeted to a page that looks something like this. So I'll give you guys about a minute or two to do that, and continue going along once everyone's done that.
Sweet, sweet. Give the audience some time.
Perfect. Thanks for facilitating this.
My pleasure. My pleasure. Looks like they're still taking time. Does anyone need more time? Or still going through it? Take that possibly as a yes. Anyone having issues? All right.
Okay, amazing. Thank you. So hopefully something like this pops up that says Cohere dashboard and welcome your name. Then under settings, you want to go to something called API keys right here, and it shows you this default API key here, shows you the last couple digits of it, and there's this little copy button here that's like the two pieces of paper on top of each other. You're just going to press that and it'll copy your API key. Then in my notebook, at this little section where we're doing some setup at the top, you would want to go and paste your API key within the quotations there. So it'll be a long list of like numbers and letters, and you would want to put it in there, and then you can run whatever you want alongside me. So as you guys do that, I'm just going to start digging into the actual notebook I have here, but please interrupt me if anyone does run into any issues. There's this Python package called Cohere that you'll need to install in order to work with these things. And again, all this stuff's really similar no matter what the provider you use is. There's usually going to be a Python package that you'll have to pip install up here, and then you'll have to import in order to actually work with stuff. And so the first endpoint we've been talking about is the generate endpoint. Here, I've pre-run my code, so I won't be running it with you guys, but let me know if you run into any issues, like I said. Here, the only required argument is just the prompt. So I want this model to generate a list of reasons why learning data science is good. And it prints out a bunch of stuff, which is sometimes a little hard to understand. So if you at all want to just see the text, that's what this next code block is for. You just specify that you want to see only the text part, and that's what it shows you. Now you might be a little confused. It's pretty incomplete. There's like one point and then like a second point that's started, but no text next to it. That's because the default value for how many tokens it spits out is just 20. So it can't produce a lot of text. And so you need to actually go in and, if you want something longer, set max tokens to something bigger. So here I've set it to 200. And then this creates a good list of reasons why you should learn data science. That's pretty exhaustive because it's had enough time to complete everything and it's not cutting off mid-sentence. Then the next thing I'll show you, I actually took from the LLM University page, where they show how you can kind of, as you vary temperature, get different outputs. So this is a function here I've just made in Python that'll basically just take in a prompt and temperature and give me some outputs. So if I put that in a loop where my prompt is generate a concise but catchy tagline for the University of Waterloo Data Science Club, and I loop over temperatures from 0 to 5, we can see how varying temperature changes the outputs. And so back at temperature 0, like expected, we get the same outputs all the time. And it's as basic as can be. Like, this is probably the most boring tagline you would see, but there's nothing wrong with it. And it's pretty professional. And then if we scroll down and go to higher temperatures, I'm going to bring us all the way to temperature of 5. You can see that it gets more interesting, like the University of Waterloo Data Science Club breaking down data walls, building up data awesomeness. That's pretty cool and creative. I would not have thought about that by myself. So this is an example of kind of how increasing temperature will increase the randomness. The last thing I'll show you is just a very light example of the sort of prompt engineering style things people do. So I've copied a bunch of text here that's just from this article from the Record in Waterloo called Wild Turkey Smashes UW Window After Canada Geese Attack. And it's just a little bit of the article there, because maybe I want the large language model to know a little bit about this event. And then I start asking it to kind of complete this part of the answer that says a poem inspired by the text above. And I want it to specifically start with, oh, the Waterloo geese. And so when I do that, I can get this nice poem that it starts with, oh, the Waterloo geese, and it does know about the tormented turkey that was troubled, tried to fly to freedom, but ended up in a room where he crashed into a wall. So all this stuff, you're giving it some context, and it's able to complete what I want a lot better. Now for classify, this example I have is, let's say I have a bunch of reviews of workshops I've given for the data science club, but they're not particularly productive and they can be kind of mean. So I don't really want to read them all. I just want to know like how many are good and how many are bad. So I have this example list where in the past I've gotten this feedback that says, oh, it's the worst, oh, it's the best, and I can classify them into being either bad reviews or good reviews. And so something saying a waste of time is definitely a bad review, whereas something saying incredibly useful is definitely a good review. And so I provided a couple examples like that, and then I can have a list of feedback that I don't know if it's good or bad. So here, I hated the data science club workshops. That's supposed to be bad, but I can automatically kind of get that as an output if I use this endpoint. So here you can kind of see that first one. I hated the data science club workshops was bad with a confidence of 0.97. So I was pretty sure it was bad, which is right. And then the workshop was helpful, was good with a confidence of 0.99. So again, it's doing what we expect it to do here, which is great. And then you can tell though that something like the data science club workshops are the best thing ever is good as expected, but with an even higher confidence of 99.6%. And something like would go again is good too, but with a lot lower of a confidence. So it's really useful tools for doing this sort of thing. We're just going to cover 3 more, but they'll be kind of short. So this is just how to use the summarizer endpoint. I've gotten a bunch of text to fill the Waterloo Data Science Club theme of really liking Taylor Swift. That's basically just from her biography up on this Britannica website. And it's in this long set of text I have out right there in this like long string. And I'm saying I just want a short summary. And what it outputs for me is just Taylor Swift is a popular American singer-songwriter whose country music has won her numerous awards and widespread critical acclaim, which is absolutely fair and a good little concise summary, but you'll probably want a bit more details than that. So I'd encourage you to run this with something like a length of medium or long and see what you get and see if it makes sense. Now, re-rank, we talked about being good to search through like a bunch of documents or little snippets of text that you have to pull out the most relevant one to a question. So this is another example we took from the Cohere website, where my query is what is the capital of the United States? And there's a bunch of words here that if we were just doing keyword search might pop up as being relevant, like capital punishment, for example. But we do want this one saying Washington, D.C. is the capital of the United States instead of capital punishment. And thankfully, when we do run that, we get that the most relevant section of text is that exact one that we were looking for. The last endpoint we're going to talk about is just detect language, which is a cute one where there's some examples showing hello world in a couple different languages. You can throw in as many more as you want. Here, the link to 74 different languages to say hello world. And then you can predict kind of what language it is. So I got English for hello world, which is right, Russian for this, and so on, so that it can kind of show you how to check which language the text is in. The last example I'll be touching on is LangChain, like I mentioned. So it also has a Python package that you would need to install and import some things from. And then if we want to use the Cohere model, all I need to do is let it know that that's like the model I'm using in a short bit of text like this. And then if we want to actually generate text, I can just use it as normal, where I have this text prompt here about how to be happy as a Waterloo student in midterm season. And just as the Cohere API would, it like if we just use it in generate, like shown above, it outputs a bunch of text like we expect it to. But one of the cool things is you're not always going to be using APIs that have something like a chatbot already built in that you can use. So they have some code already ready where you can do something like a chatbot and not just kind of copy the text that's already been talked about into the prompt, but actually make some summarization of what's been talked about, put that into the prompt, and then continue to interact with it. So that's really useful if you do want to have longer chat conversations that are maybe longer than the amount of tokens the model can kind of take as an input. So there's some examples of me using it here and the chatbot being able to talk back to me. So hopefully you guys have learned quite a bit today. If you're interested in learning more, like as already been mentioned, this is a link to the Cohere LLM University where a lot of these examples were taken from, so you can kind of dive deeper on some of this stuff. Last week, we ran a workshop touching on transformers that you can find up on YouTube at the link below there. And then in general, there's always some good data science resources on our club website, which is here. So I'll ask if you guys have any questions, and I'll ask if any of the cakes here, and I should just shut up and get to the questions later.
Now we're still waiting on the cake, so we can answer a few questions. And of course, give a round of applause in the meantime. Sweet seat. Got a question from Blue Sweater over there. Oh, okay. He's saying in the notebook the LangChain part might be missing, or is it somewhere else? Is there another section?
I think it's just at the bottom. There's a heading called LangChain, and I haven't done too much with it here. All I did was this, like this is me using LangChain. Just it's kind of a wrapper for the Cohere model. So when you see me kind of calling Cohere with some text, that's me using LangChain and just telling it I want to be using the Cohere model for that. And the one thing I'll just pull up just so you guys see, because I haven't done it all an exhaustive thing here, but they have a really good handbook where there's an outline of kind of all the different things you can do. So when I was mentioning the calculator, that's this chapter 6 here, where you can kind of see a walkthrough of how they actually give it access to a calculator to do some math. But yeah, apologies, it's not too exhaustive what I have going on there.
No, I'm saying, like, is that notebook different from ours?
He's saying if this notebook is different than.
With like fine tuning, nothing in it, and then no comments.
Okay, he's saying his notebook ends with like fine tuning and then nothing else afterwards. Is that a different one or?
Oh, one sec. I'll fix that in just 1 second, okay?
All right, sweet.
And from what I understand, the cakes outside, I'll fix this in the link. And then when they go check the link, they'll see the correct notebook.
All right, sweet. Do we have any more questions? If not, I don't know if you were actually able to see everyone, Luis, but the whole audience and stuff. Oh, still down? All right, there we go. Oh yeah, that's the useful.
Well, hi everybody. Nice.
Hey. All right. Yeah, without further ado, yeah. Thank you so much. And I think I can speak for everyone else here. Yeah. We're all pretty appreciative of this talk. One last round of applause, everyone.
Thank you, everybody. Ashley, your presentation was awesome. I learned stuff. Okay. Yeah. Thank you.
Thank you. I really enjoyed your presentation.
All right, sweet. Take care, everyone.
Bye.